Hi everyone, I'm Andy Catlin. I teach in CUNY's MSDA program. The MSDA program is a challenging master's in data science designed to give you project-based experience building complex, relevant, predictive and prescriptive applications in R and Python. Please let us know if you're interested in learning more about the program. It's my pleasure today to introduce the speaker, Thomas Quintana. Thomas is an open source geek, maker, and evangelist with over a decade of experience building distributed systems and a little over 3 years working with statistical models to build out high-value production systems. Thomas has also organized the Fort Lauderdale Machine Learning Meetup, where I met him, where data scientists from Miami to Tampa come together for jam sessions to meet and learn more about neural networks, deep learning, and related topics. Thomas.
Thank you, Andy. I really appreciate that introduction. Hello, I hope everyone is doing well. As Andy just stated, my name is Thomas, and today we are going to cover a brief introduction into Google's TensorFlow. Before I begin, I'm going to say a few things about myself. I have quite a bit of experience building distributed systems in the telecom industry. As Andy stated, a little over 3 years building production quality statistical models. Big open source geek. I've contributed to quite a few projects and started a few of my own, including Ruscom, which is an open source implementation of Twilio. I really like the startup scene, and also the founder of the Fort Lauderdale Machine Learning Meetup Group, as was already stated, which is how I came to give this talk. So let's look at the agenda for today's talk. We're going to ask why we care about Google putting out another deep learning framework, considering there's so many already out there. We're going to talk about what TensorFlow really is, what the programming model looks like. We're going to cover underlying implementations that that'll make more sense when we get to that point, and a few extensions that were added to make our life easier. Finally, we're going to conclude with an example in TensorFlow so that we can get an idea of how all of this comes together. Great. So a great question to ask is, why do we care that TensorFlow is out? If we look out in the open source community and in the machine learning community in general, we can see that there's a lot of frameworks out there that already enable us to build machine learning models. For example, there's Theano from the University of Montreal. There's Torch from Facebook's AI Labs. There's Keras and a myriad of other frameworks from the open source community and industry alike to make it better. So here are a few points as to why I think TensorFlow fills in some missing gaps and brings a lot of value that wasn't already present. One, it really decouples the implementation from the platform or language that we use to build these models. So out of the box, Google supports Python and C++, but a lot of community projects are coming up for Java, Rust. I'm collaborating with a gentleman at Microsoft who's looking to build bindings in F#, and that lowers the learning curve that we would need to start working with these models and taking advantage of TensorFlow. Another interesting detail about TensorFlow is that because they decouple the implementation from building the models, you have a situation where we can have implementations that run for mobile devices up to large clusters of high-end GPU servers. And I'm not aware of how many of you follow up with TensorFlow, but there was recently an article on TPU, which is hardware accelerators that Google's been working on with TensorFlow in mind that'll give us great improvements. And we're not limited to these devices. We can continue to add implementations for as many devices as we like. That's very powerful. TensorFlow is also interesting because you can use the same framework for research and production systems. Typically the way things are done now is researchers do research in Python, primarily Theano and Torch, and then when they're ready to go to production, they hand over specs to an engineering team that basically re-implement the system in something like C++, so they can take advantage of GPUs and hardware acceleration, which makes it much more difficult to go from research to production. I think the biggest benefit that TensorFlow brings is that it allows for distributed computation. Up to now, most of the frameworks out there for machine learning research only allow you to run on one machine. So when your models get really large, it becomes very difficult to scale because you have to build all the scaffolding to make sure that you can train a model in a distributed fashion. And lastly, Google is one of the leading companies in the world when it comes to implementing statistical models and deploying them into production. They have the right skill set and they have all the resources to make it a great product, which I think is a big deal, as opposed to some of the open source community projects that don't have that kind of backing and therefore aren't as complete. So I alluded a little bit to what TensorFlow is in the last slide, but we're going to properly define it now. So TensorFlow is two things. TensorFlow is an interface for expressing these machine learning algorithms that we want to implement, but it's also an implementation. And the reason we need to talk about these differently is because this decoupling is what allows us to build models that run on heterogeneous hardware. And it also has some important implications. For example, because of the way it was designed, it's very easy to extend TensorFlow to either support new hardware or add new front-end or client languages to build these models in. And that all brings a lot of benefit to the research community and the practicing machine learning community. So there is a graphic here that should be rendering. So TensorFlow has, let me see, I apologize for that. Okay, so the TensorFlow programming model is a model that allows you to build data flow graphs that express some mathematical computation that you want executed on n-dimensional matrices, right, which are called tensors. And the way we do this is TensorFlow exposes an API for us to build the nodes of these graphs. And once we have a graph put together, we can use what's called a session to actually have TensorFlow figure out how to place the nodes in the graph on hardware for execution in order for us to either train a model or perform some kind of inference. So let's talk about some of the key concepts when building these graphs and working with TensorFlow. So an operation and a kernel are tightly coupled in that an operation is some abstract computation that you want to perform on tensors. For example, you may want to add two tensors or multiply them together or compute the dot product. And a kernel actually implements these operations on the specific hardware that it's going to be run on. So you can see these two are very tightly coupled. Sessions are the way that clients interact with TensorFlow, that we basically ask TensorFlow to execute some computation graph on our behalf. So whenever you're going to work with TensorFlow, it's always going to happen in the context of a session. Also, we have tensors. For those of you that are not familiar, A tensor is a typed n-dimensional array that flows along the edges of the computation graph, and that's how we got the name TensorFlow. Right? These matrices flow through these computation graphs as they get transformed at each of the nodes. And lastly, we have a variable. A variable is a special kind of operation that just returns a handle to a persistent tensor, right? Which is just a tensor that survives, whose state is kept between executions of a graph. And an example of where this is important and necessary is if you're training a neural network, you want your weights to be able to survive all the iterations when you're training, right? You don't want them to be reset. So it's a pretty good example. So what I've done is I've actually put together a Python notebook for us to go over what some of this, what TensorFlow looks like, how you build these nodes, and how you use a session to execute this graph. So we're gonna basically go over the infamous hello world example, but for TensorFlow. And what we see is here is that with the with statement, we start a new session, and we use this session to construct a graph of a single node that returns a constant string, or returns a constant string called that has hello TensorFlow in it. And if we run this, what you see is we created a new graph. We handed it off to a session, and we had TensorFlow executed for us. Now, I know that's not very interesting, but it kind of covers the key components of how you would use TensorFlow. All right, let's do something a little bit more interesting. In this case, we're going to work with a variable. So what we're going to do is we're going to build a countdown latch, right, where we create a node of type variable that maintains its state between graph calls. We're going to define a constant number 1, which is what we're going to decrement our latch by. And then we're going to apply a subtraction operation. And lastly, we're going to update the state of our latch. Now, an important note to make is that when you're working with TensorFlow, variables, so at this point in time, the variable latch is not initialized to the value 10. So if we were to run this example without before calling initialize all variables, TensorFlow would actually give you an exception. And the reason being is we need to run this operation first so that it basically tells TensorFlow initialize the variables to values that we passed in as in the constructor. So let's see what this looks like. So we start a new session, right? Because we can only run a graph in the context of a session. This is the operation that I was talking about, where we initialize all the variables, and then finally we count down on our latch. And you can see that the results of our example here. Now, just as an example, what we're going to do is we're going to comment out this line, and we're going to rerun this script. And you can see that TensorFlow basically gave us an exception that because the variable itself was not properly initialized before we started using it inside the graph. So that's a good note to make. All right, so that's great. Now we're going to try to feed some data into a graph to kind of get out of playing with toy data or data that we've kind of just defined statically within the graph. So when we build a graph, we want to pass in training data or a data that it hasn't seen before, so it can make so the graph or the model can make an inference. In this case, what you want to do is you want to provide a dictionary that has the data that's going to be pre-populated into the respective nodes. So here's an example. What we want to do is we want to define a graph that multiplies 2 nodes and returns the output. So we do that here, and if you can see here, each node, all the nodes have attributes, and in TensorFlow, attributes are a good use of them is to make nodes polymorphic. So in this case, we're basically telling it that we want to put a floating point value inside of these nodes, or these nodes are going to be holding floating point values. And so once the graph is built, the first argument to the run method of a session is an array of the outputs that you would want from the graph, and this feedDict argument has a dictionary of the values that you want to pass in. In this case, you're going to put the value 5 into A and the value 5 into B and multiply them together. And you can see that we get a NumPy array back with 25, and we maintain the proper type. Now, in this other example, basically what we did is the same, very similar to the last one. It's just more of a demonstration of pulling stuff out of the TensorFlow graph, right? Basically what we're telling is we want to add and multiply the values that are being passed in, but instead of retrieving back just one value from the graph, or one tensor, we want more than one. And we can do that with TensorFlow. We can tell it that we want more than one value. Now, an interesting note about this example is that we have a graph with 2 nodes, and we can actually compute, this is a much simpler graph, but we can compute subgraphs of a bigger graph. And this is important because sometimes when you're testing your model, you just want to test a little piece of it, and you don't want to run the entire graph, especially as the models get more complex. So this lets you break your graph into subgraphs that you can execute separately. All right. All right. So let's talk about the underlying implementation of TensorFlow. So as I stated earlier, TensorFlow is separated or decoupled into an interface and an implementation. Now, the client talks to the master using a session, right? And then the master manages a set of worker processes. Each of these processes is responsible for one or many GPUs. Now, this is important because before the recent release of TensorFlow 0.8, we didn't have distributed graphs yet implemented inside of TensorFlow, but it was recently released. And so now we finally do have two implementations. The thing to note is that the distributed implementation shares most of the code with the local implementation, something that's self-contained. It just adds extensions for distributed computation. And most of what that means is that it replaces nodes where there's a break in the graph with what's called a send and a receive node. And these allow them to share information inside of a cluster. Let me show you a picture of what this looks like. So in a single process or on a single host, you have a client process that uses a session to talk to a master, which will execute a subgraph. Now the way that this happens is TensorFlow uses a greedy algorithm to figure out a cost model for executing your graph. Now, this cost model may be based on heuristics, or it may be based on a previous pass over the graph. And then based on this cost model, it figures out how to split up nodes onto specific devices themselves. And once TensorFlow knows how to put the nodes on the specific devices, it'll split up your subgraphs into chunks that it sends out to different hosts for processing. And you can see a better example of that here, right? On the right-hand side, where we have multiple worker processes driven by one master process. Now, TensorFlow has put together a few extensions, has added a few extensions to a computation graph, which you typically don't see, but make our life a lot easier. Probably the most important extension to TensorFlow is automatic differentiation, which computes gradients, for example, a cost function with respect to some input x automatically for us. So as our models get more and more complex, we have computing the derivatives for the gradient becomes more and more difficult and a big source of errors in models. So automatic differentiation is really, really key, especially in deep learning. I actually brought up the fact that partial execution was possible previously when we were going over the Python book. This is very interesting because Theano has a similar model where you can build a computation graph, and TensorFlow implemented the same model, and what happens is it makes it very easy to test your code, which in statistical models is not always the easiest of tasks. So another extension is known as device constraints, and TensorFlow actually allows the client to specify where the client wants to place nodes for execution or on what device. A good example of this is if you're going to do a large matrix multiplication. Even though TensorFlow would make the right decision, you can actually tell TensorFlow you only want to execute that operation on, for example, a GPU or FPGA device, because you know it's going to be faster. So TensorFlow also provides some control flow nodes, which are not common at all in computation graphs, but do provide the ability to implement some algorithms that are not easy to express in linear algebra terms. So input operations is interesting in that when we were going over some of the examples, there's not a lot of data. But when you start building real-world models, the more data you have to train the models, the more accurate they become, and the better they are at making inferences. So input operations are special operations that we can implement to feed data into TensorFlow. A good example is on a project that I worked on, we had our data split up over many Hadoop nodes in a cluster. In this case, we would implement an input operation that feeds data from Hadoop directly into TensorFlow as an example for training the model, which is very useful, and it makes things much more efficient. So we have two more extensions. Okay, so queues were added into TensorFlow. They have interesting properties in that they're blocking. So I personally have used queues in concert with input operations as a way to push data into the graphs, right? So we allocate a block, we push it, and then we block and wait the graph to process that data before we put more stuff into the queue, as an example. And now lastly, containers are a mechanism that TensorFlow uses to implement any kind of long-lived state. So when we build a variable node, where TensorFlow actually uses a container to back that variable node which maintains its persistent state across calls into the graph. And I know that this is very brief. I highly suggest that everyone read the TensorFlow paper. There's a lot more to discuss in respect to these extensions, but some of these extensions alone could be a talk on their own. But these are the things to look for when you're working with TensorFlow. All right, so automatic differentiation. I thought it was such a big deal that I added one more slide so we can kind of get an idea of how TensorFlow does something like this. So let's assume that we want to know what the gradient is with respect to the input from a neural network. So what TensorFlow does is it does a forward pass from that dependent variable. I'm sorry, from the inputs, sorry, to the cost function, and then starts working its way back. And at each node, what it does is it introduces another node into your graph at each, it introduces another node into your graph which computes the partial derivative for, in this case, the cost function with respect to those inputs at that state in the graph. And it keeps doing that all the way down to the input, as you can see, which is how it computes our gradients on our behalf for us. Now, there's something to say about this. So a lot of the examples that I use are in works, because a lot of the work that I'm doing right now is in deep learning. And an important thing to keep in mind is when you have automatic differentiation, it can be very expensive in terms of memory resources. And most of us train our models on GPUs. And GPUs, the biggest issue with GPUs is we have very limited memory. On the Titan X, which is the card that I use to train my models, we have 12 gigs of RAM. And so there's still a lot of room for optimization inside of TensorFlow on how they reuse this memory, right, which is our most precious resource because it's very limited. All right. All right, so let's look at, so we spoke about some of the extensions. So one of the extensions that's that we're going to talk about right now is device constraints. And the reason this is important to cover is, so TensorFlow does a lot of work for us out of the box, but whenever we're going to, if we have a single box or a single server with multiple GPUs inside of it, it's up to us to tell TensorFlow how to break up the model so that it can be executed across multiple GPUs on your box. Right. Now, on the box that I'm giving this talk right now, there's no GPUs. So what I've done is I've commented out up here what it would look like if you were going to use a GPU. And we're going to basically add constraints on which to run a graph. So I'm running this Python book on a dual core virtual machine. And what we can do is we can tell TensorFlow that we want to execute our graph on just the first core and not use the second core. Likewise, if you were using a GPU, you can say, I would like to execute a section of my graph U0 and another section that doesn't have a data dependency on a separate GPU to make simultaneous progress, or as much progress as possible on the graph. And so if we run this, we see that we get the right answer. So what's going on here is we're basically telling TensorFlow that we want to use the CPU 0 and these are how the labels are used. And we're going to do a matrix multiplication on this CPU. Now, if we wanted to, we can have multiple statements with different CPUs that we want to execute stuff on. And it would split up the graph so that it executes the way that we've specified it. Now, an interesting question that I was asked is what happens if, for example, you have one GPU and you specify the second GPU. And so what I have here is, since I have dual cores, I'm going to ask TensorFlow to try to run it on a third core and see what it does. And as you can see, it says it can't assign it to that node because it doesn't exist. So TensorFlow knows what hardware you're running and make sure that we don't make mistakes like that where we ask it to run something that doesn't exist. Lastly, I know we've covered a bunch of little pieces, and what I like to do is I like to wrap up with an example that kind of brings it all together. So here what we did is I implemented a nearest neighbor algorithm with TensorFlow. The algorithm itself is not that important. In the context of this talk, what's important is to kind of see how all of these things that we were talking about come together. So we're going to go over this little piece of code briefly, and then I'm going to open it up to questions. So for those of you who are not familiar, MNIST is a data set of handwritten digits produced at Bell Labs by Jan LeCun. And it's pretty much a de facto data set, at least when we're talking about vision problems. And you're going to see lots of references to this framework, or sorry, this data set out in the field. Okay, so the first thing we do is these images come in as matrices, so we squash them into one-dimensional arrays or tensors. And the graph is pretty simple. Basically, we have a list of all the neighbors and an input x that we want to make an inference of. We compute the Manhattan distance, which is not important in this particular conversation. And then we make an inference based on the nearest neighbor, right? So to summarize, we compute a distance function from our input to all of its neighbors, and then we pick the closest neighbor as the class for our input. Once again, we want to make sure that we initialize the state of all the variables. And once that's done, we're going to loop over the training data, making inferences of it, and print how accurate our model is doing. And if we give this a second, it just downloaded the data set. And there we go. We have, and you can see here that the model is doing 99% accuracy on this data set. On the slides, I'm not sure where they're going to be made available, but I can make them available as well. There are links to this Python notebook. So for those of you who kind of want to go and play with this stuff and have access to the slides in the notebook, it will be made available, and you guys can kind of tweak this stuff and see what you come up with. Alrighty. Alright, so a few resources. I highly recommend the TensorFlow paper. It goes into much more detail on every single thing that we covered. The TensorFlow website is really informative. It has a lot of neat tutorials on vision networks, recurrent neural networks. I think one of their examples does language translation, which is really interesting. So I highly recommend following those along. Those of you who learn better by watching videos, Udacity has a deep learning course in collaboration with Google, and that course is taught using TensorFlow. And then lastly, you can go to the GitHub repository for the TensorFlow project to get more up-to-date stuff on what's going on. And also keep in mind it's a good idea to probably join the mailing list. All right, so I'm going to open it up for questions. But before then, if you guys have any more questions about this talk, the examples, if you guys feel like you're stuck, please feel free to reach out to me. I'll do my best to help you work through any questions or problems you may have. And if you have any questions about the data analytics program at CUNY, please either go to the website or send an email to the address that's provided here. All right, so that is the conclusion of my talk, and I am open for questions.
Hi, so Thomas, so people aren't able to, as you might have guessed, people aren't able to actually talk because their mics aren't enabled. So for anyone who's listening, please type into the chat box. There should be like an area for your questions that you can type in. And we'll just wait a second. So
yeah, I'm. Oh, okay. All
yeah,
right. So
there
here's a
should be like
question.
a.
How do I? I'm sorry.
No, it's okay. You got it. I was gonna say
Oh,
there's
okay.
like a little window that you can click open where all the questions go into. Go for it.
Oh, got it.
Go for
Appreciate
it.
it.
No problem.
All right. So how do I rate CNTK? So I think that it's really comparing apples to oranges, and here's the reason why. So Microsoft CNTK is definitely a great platform, but it reminds me more of something, I don't know if you're familiar with Caffe. So here's where it comes down to. Right now, CNTK has numbers that they're faster than TensorFlow on a single box. But CNTK currently doesn't have a roadmap or a path with distributed models in mind. And so on a single box, CNTK may outperform TensorFlow, but the moment you start getting into large data sets, you want to use a cluster of servers anyways, at which point you're no longer comparing apples to apples, since CNTK is kind of stuck to a box. Another thing that I'm not crazy about with CNTK is that CNTK defines what they call a network description language, which is something that's proprietary, not proprietary, but specific to that framework. And so it kind of binds you to it. I personally like the approach of having many front ends in like C++, F#, Python, so on and so forth, as a way to build these models. Because if they don't support something that you want, it's kind of out of the question unless you want to contribute it back to the project or they implement it. I hope that helps answer the question. CAFE. Okay, so CAFE is a computer vision framework out of University of Berkeley. It's a very, very stable project, and every single ImageNet model has been implemented in CAFE. All the Google Inception networks. I'm not sure if the recent Microsoft winner has been implemented in CAFE, but I think it's a very interesting project and one to look at. CAFE as well defines their own network description language that you use to define models. The only difference is that CAFE actually provides Python bindings alongside their description language or network description language. So we have the option of using Python, which is pretty standard in the research community. Still would like more options like TensorFlow. Any additional questions? My pleasure, by the way. I think we're done then. All right, guys, have a great day.